Okay, let's continue now with the part where we're borrowing the bits. We've established that it's Class C, we established that the structure is network, host, default mask, all ones under these ends means 255, 255, 255.0. 0 because there are any host bits. Network portion is only indicated by ones in the network portion. This indicates no network portion, but we're going to change all that. Notice that we've got our last octet to choose from. We realised from before that we need 4 bits. 2 to the power of 4 minus whatever is still 10 subnets available. So we're looking now at the last octet, and we're going to blow that out and have a look at what that looks like blown out. And in a binary pattern, we have 128, a 64, 32, a 16, an 8, a 4, a 2, and 1. Halving as we go down, doubling as we go up. That never changes. So that represents our 8 host bits. But we're going to borrow 4 bits, so instead of an H now, we're taking that away and saying, no, you're an N. Because we want to borrow you to make more networks. Make sense? We need more N's to make more networks. These last 4 bits are still designated host bits. So you can see indicated under here, the numbers are important. Do this every time. Designate how many bits you borrow, and as soon as you've designated the last bit to borrow, we always borrow left to right. So we borrow from 128 across, left to right. Now we see here that it stops basically between 16 and 8, the 4th and the 5th bit going this way. So we divide that to make it clear that's where our borrowing ends. That's where we stop borrowing our network bits, or taking H's and turning them into N's. And now all we have to do is designate our subnet addresses. We started with one network number, so in this scenario we have the old system where that would be just that network here, such as 192.11.10, and there'd be all these addresses on that network. Too much congestion at times, having just one network to manage all your hosts. We want to break it up. That's the point of subnetting. So we carry on now, and we just use our binary system, our counting system, to designate our numbers. Starting with the least significant bit borrowed, this is this bit under the 16, we just simply go 0, 1, 0, 1, 0, 1, and so on. And you can keep going depending on how many we need to find. Following that, we go under 32 and place 2 zeros, 2 ones, 2 zeros, 2 ones. And you'll see a pattern arising here just from counting in binary, 4 zeros, 4 ones. And this would be 8 zeros, and I'll just use that quick method to show you that's 8 zeros, and then there'll be a 8 ones going down that way. So what we've done is easily indicated our subnets, our roads. Instead of having this one road now, we're going to turn it into 10 roads. So let's say that's our first, that's our second, that's our third, fourth, fifth, sixth, 7th, 8th, and 9th. So our first road is this road here. Notice subnet 0. And that would actually look exactly like that. And that's why we're talking about taking those 2 possible subnets off, the one that's all ones down here, be one we wouldn't use, and the zeros, but we can use the zeros. The second subnet, or subnet 1, in this case, we can find out exactly what that value is because on this row we only see a 1 placed under the 16. So the road actually would become, if we use subnet 1 as our first road, let's do that, we see it'll be 192, oops, so you write 6, 192.111.16. That's subnet number 1. You'll notice that to find the next one, we look in the next row of digits and we see a 1, and only a 1 there, placed under 32. So that'll be our next road, 192.11.1.32. Same 3 numbers, that never changes because remember this structure is stuck, it's fixed. We will always keep that. But where it changes is the last octet, indicated here. And so on. So that's 2, this is subnet 3, subnet 4, subnet 5, subnet 6, 6, subnet 7. And you'll notice that to find the third usable subnet, if we weren't allowed to use subnet 0, we find there's a 1 in this position and a 1 in this position, falling under 16 and falling under 32. So we see that it's 48. I might just use X, X, X to indicate they're not changing those numbers. 192.11.1 doesn't change, it's only the last octet in this structure. So we see under this we've got the next subnet number 4, that one falls under 64, so it's 64. And hopefully you can see an increment here between the roads, or paths, or routes. Between 16 and 32, we have a difference of 16. Between 32 and 48, a difference of 16. And so on, so on. So I could stop looking at this basically, even after I find the first one. It always goes up by the first increment. So I see here, 16 plus 64 is 80. 16 plus 80 is 96. And so on. We can find as many as we need to go by doing the 16s. Not too difficult, I hope, mathematically. So we've found our roads. So on a router, the router will use this information, particularly our mask. Now we haven't talked about the new mask as such. If I place a 1 under all ends, remember that will indicate my mask. In a Class C environment, a normal mask was 255.255.255.0 because this last portion was a 0. We borrowed bits now. So what is our new mask? And we see by adding the values where 1s fall, and that's where we have to put all 1s in the network portion, we see 128 plus 64 plus 32 plus 16. And that in fact equals 240. So that plus that plus that plus that is actually equal to 240. So our new mask, which is vital to the router's configuration, is as follows. 255, 255, 255, 240. So when I configure the interface and various parts of the router, the interfaces, I need to use this mask. It's going to be the same mask. We're using classful subnetting. So the mask is continuous throughout each road. It's only the road beginnings that end, that differ. And we'll talk a little bit more about the rest of this situation.